just jump into the class stuff then. Last time we talked a little bit about linked list, and then we went over the operations really quick, and we got partway through programming an example of a linked list, and I think we just did the insert, and then we still had the lookup and deletion. Let's go ahead and finish that, and then let's talk about alternatives to doing that, and then maybe just some advantages of a linked list. But first things first, let's just refresh on what a linked list is. So remember, we have this general object that you're going to see a lot if you take stuff like data structures. It's called a node. And it contains two things. It contains data, which could be literally anything. It's just an integer or a float or a pointer to a class or a class object or a linked list. You can put anything in there. Just represents some sort of data that you want to store. And then we keep in the second cell here a pointer to some other node. So generally that's to another node. And we can, if we're doing a linked list, kind of chain these together until we reach the end of the linked list. And then we said that we put a null at the end of the linked list to signify that it points to nothing else. So we kind of have like a train-esque structure where these are all like connected together and they're all linked in one way. And as far as the current structure that we only have one pointer, and that pointer is going to always point to whatever the next node is. And then we said when we're doing a linked list that on top of this series of nodes, we're going to keep a pointer to the head of the node, or the head of the list, which is just the first node in our list. That way we know where to start. And then we went over how to insert, how to delete from this thing, and then how to look up as well. So I think we did insert last time. What I want to do then is the lookup, which is pretty easy, and then the deletion, which I think is the hardest one, but it's really not that bad. So the lookup, what we want to be able to do is go and grab one of these nodes, either the element that is there, or a pointer to the node itself, or a Boolean just saying something is there, and be able to tell that something is in our list. So let's say we had an integer linked list again, and this is like 4, 6, and 7. So let's say I'm looking for the number 6. And we have a couple different strategies for this. One would be if the lookup we wanted was just get an element at a specific point, then we could index these. So this would be the 0th linked list, or 0th node, first node, second node. And then if we have that head pointer, then what we can do is, if we ever wanted to get this, all we have to do is follow the pointer as many times as the index we want to go to. So remember, if we start at the head, then we have to do 0 hops in order to get to the 0th element. If we want to get to the first element, we have to follow 1 pointer. So we start at the head, just follow this once, and we end up at position 1. And if we wanted to get to position 2, we would follow it 2 times, and etc. for however many hops we want to do. So if that's the kind of lookup that you're trying to do, it's pretty easy. If we're trying to look up an element itself, it's also not that bad. So if we were to look up the number 6, then what we do is we start at the head and then check, is this thing there? And if not, we follow the pointer to the next one, and we just keep checking. Okay, so we said we were going to finish typing that up. We had 2 classes. We had a node class, which just had that data that we mentioned, which I have as a generic type. It's just T, whatever type that is. We'll fill it in later. And then we have a linked list class, which is also of generic type called T. And it's going to be the same thing. It just has a node that represents the head. So we have this node class here, and then we had in the list class, we just had that head that we said, so a pointer to where the list starts, and then these 3 functions and a constructor that just initializes it to be empty by setting the head equal to null. So we finished the insertion. Let's go ahead and do the lookup, which won't be too bad. It's going to be essentially the same code that we did last time, where we had some sort of traversal. Essentially this code right here, we really just have to modify it. So what we're going to do is we're going to set it equal to the head by default. We're going to keep track of some pointer to the current node that we're looking at in our linked list, and then just update it to go to each successive node in our list. Start at the head, and then what we do is we check if the pointer to the next object is not null. Then that means that there is a pointer that we can follow, that arrow coming out of the right of each node. Then we're going to follow it. Now we just need to modify a few things here. So this is our kind of like update condition. This just moves along our node. But since we are doing a lookup, what we need to do is we need to actually check if the current node that we're on contains the thing we're looking for. So we have some sort of object. Again, we're using a generic type because we're saying we could store anything in here, but this could be like the integer that we had in our notes earlier. And we need to check if that matches the object at the current place. So what we'll do is check if that object is equal to the current data. And if so, then we know that that's a match, and we can return, I think we decided to return a pointer to the node where it belongs. In this case, that would be the current node, because that's the one that matched it. So if we find the data is essentially what this says, then return it. And depending on your use, you might not return a node pointer, you might return the data itself, or just a Boolean saying that the thing is there. I'm just doing it kind of like a generic thing, but really the code would be the same, it would just be what you return. And then this was our update, we said. And then we need one last thing. So if we go through the whole list and we don't find a match, then we should probably return something just to signify that there was nothing there. And because this is a pointer to something, I think the most reasonable thing to do would just be to return a null. Or you could throw an exception as well, just say like not found. That would be fine. I'm just going to return a null pointer because I think that's fair and it won't crash the program if we don't find something. So that should be pretty much it. So basically the same code as this, right? The only exception was that we didn't have to check if the head was null in this case. So we did in our insertion because we would have to update our head pointer. But when we do a lookup, it really just looks through the array and doesn't have to, or sorry, not the array, the linked list, and it doesn't modify the shape of it at all, right? It doesn't add anything onto it or put something in the middle or delete anything. So there's nothing really too concerning to worry about, no edge cases that we have to concern ourselves with. Right, then the last thing we had was the deletion, which we do have an edge case, so we're going to have to consider it. But we said with our linked list, if we were to delete just kind of a normal node in this, where we have a linked list like this, then if I wanted to say delete this one, let's say this is 7, and I say delete, or yeah, I guess I would probably just call the function delete 7. What we want to do is we want to figure out where this thing is, and then just remove it from the list. But if you remember last time, we said we can't just do that straight up, because if we do that, then the pointer from the last object is going to be pointing to where this node used to be in memory, and then we have a dangling pointer, but we've also lost track of all of this stuff to the right of wherever we're deleting because we got rid of this pointer, and we essentially just lost everything to the right of this. So what we need to do is wrap this around so that whatever was to the left of what we're deleting is now pointing to the right of it. Basically, kind of excise it from our list and then update the pointers, and then we can actually do the delete keyword to remove it from memory. And so in order to do that, what we're going to need to do is keep track of some sort of pointer to whatever the previous thing is before we found our thing. And then as soon as we do that, we're going to need to update the previous's pointer to point to the thing that would be to the right of what we're deleting, and then we're just done. So that's all we really have to do. Although, I guess, really quick while we're still here, we did say that there's an exception to this. Because of the fact that it always relies on there being a previous thing, then we do have one edge case, and that's if the thing we're deleting has nothing to the left of it. So no previous node that exists, and the only time that would happen right, is if we have something like this, where the thing we're trying to delete is the head of the list, in which case we have to both update the head pointer because we're doing something with that, and then also we need to just remove this. So there's nothing to the left of this, therefore we can't update like a previous pointer, and we have kind of a special case. So we'll need to check for that first, and then we can just do the normal deletion totally fine. Okay, so what I'm going to do is just first check if it's the head case. And if that's the case, then what we need to do is we need to first keep track of a temporary pointer to whatever the previous thing is, or the previous head, that is. So we'll keep track of that. We will then set the head equal to the current head's next. So we're going to have it point to whatever the second element in the list is instead of the current head. That way it goes around it. And then we can delete the old head. And so this is just so we don't lose reference to it by either deleting it too early or by doing this operation. I'm sure there's another way you could do this, but I think this is a pretty simple way to do it in my opinion. So we'll do it this way. And then otherwise, we're going to have to do the normal deletion, in which case we will keep track of a pointer to whatever the previous node was. I'm going to initialize that to be the head. And we know that the head doesn't keep the data because it failed this if check. And so we can assume that we can start checking at the node after that one. On that note, I'm going to make a pointer, and I'm going to call it current, and it's going to point to the next. In other words, it's going to point to the first, or like the second element at index 1, that is. Okay, and then we can really just do the same exact loop that we had last time, which was while current next does not equal null. In other words, while we're not at the end of the list, then we can keep checking. So what we want to check is if we found the match, I gotta make sure to put equal. If we found a match, then we know that's what we want to delete. So let's do that deletion code we mentioned. And we said for the deletion code, what we were going to do is we were going to take the previous node and we were going to update its pointer to be the pointer of the thing that we're deleting, so that it kind of wraps around it and points to the thing that was to the right of what we're deleting. So we can do this. We can make the previous node point to the current node's next pointer, which is just the pointer to the right list. And then really that's it. We just gotta delete current, and then I would say we'll just break. Actually, sorry, not break. Return would be fine. I guess either is okay. I'm going to return just because we're in a function. I think that's probably easier. Otherwise, we know we need to keep looking through the list, and we need to update in such a way that we traverse the list in the same way that we've been doing here. So we need to do this exact same code. Just set the current node we're looking at equal to the next one. And then we'll do the same thing with the next node. And again, there are multiple ways you can do this. I just think this is fairly easy. You can do this in 2 lines, I'm sure, a different way as well. So we're just basically going to make them go 1 node to the right. To whatever the current node was pointing at, that becomes the new node for both the current and the... Did I say next node? I'm sorry, I meant previous node. Okay, So I think that covers the 3 operations. Let's just throw in one extra function here just so we can actually verify that this works. I'm just going to make a function called void prints. It just goes through and prints the list. And it's got to be a template, so I got to do this. And you'll notice that we're pretty much just going to reuse the same code here that we have for all the other functions. We're just going to keep track of some node that points to the current one and then update it and do a while loop. So I have it point to the head, we'll make sure we're not at the end, and then we'll update it every time, and the only difference here is that we're just going to see out. Let's do it this way. I'm thinking actually this is not going to print the last item if I do it that way. I think I'm meaning to do this. I should actually probably double check the other ones then. So while current next does not equal null. Yeah, it's probably better if I just do it this way. Let's just make sure that the current thing is not null. I think we would stop one early if we did that. The only exception was this one. Yeah, so, sorry, I think it's just because I was copying and pasting. But we would want to check if the current is null because that would check the last one on top of it. If we check the next to be null, then it doesn't include the last one. But if we check just if it is null, then that's when we hit the actual end of the list. Okay, so let's go to main really quick and just see if this works. So we'll make a list. I think I actually need to include the code we wrote. List.h. And then we'll just make a list of integers like we said. List of integers, and we'll just call it list. And then we have a function called insert. Let's go ahead and insert some of these things. And then we'll print it to make sure that it works. And then I guess let's just make sure that the lookup function works. So what we'll do is we'll check if list.lookup, and then we'll just check, I guess, the number 7, see if that works. If list.lookup 7 does not equal null pointer, since we said we would return that if it didn't find it, then see out found 7 in the list. And then I guess we'll just do another one just for checking if something is not in the list. So I don't know, we'll check for the number 11, which is not in our list. And then, I don't know, let's just double check our deletion. So we'll say dot deletes. I call it deletion for some reason, but I think deletion makes, or delete makes more sense. That's fine. We'll just call this 2. And then we'll do another deletion just to make sure that it works. And we'll delete the head. And then we will print the list. So hopefully this will work. We'll just double check. Null identifier not found. I assume that's because I'm not using namespace standard. No? Does it want null pointer? Okay, it doesn't seem to like the fact that I'm using this. Oh, I also don't have namespace standard here. I can't imagine why. Oh well. That's saying I can't find C out? Oh. Did I not include... I do... Oh, whoops. I don't have IOStream. Okay. Now we have something related to... list int void. I think it's saying the constructor doesn't exist. Maybe it's because it didn't put a thing here. No? Let me just try putting the code that we wrote in the class itself. I'm wondering if my syntax is just bad on this template class. Nope, doesn't seem to like that either. We might just have to change t to integer for now and see if it works. Unresolved external insert. It's resolved right here. I think I'm just going to be lazy and just make this an integer for right now. I'll try to fix this before I put it on canvas. These are going to have to remove this stuff. And we're not going to be able to do this. I'm going to have to change every capital T to an int. Am I missing something? Oh. Right, we did this. Sorry about this. I don't know why it's not liking my template class. Okay, now I think the only exception here is this one, in which it's saying you can't use an integer to construct an integer node for some reason. A value of type int cannot be used to initialize an entity of, and I don't know why. If I just say node pointer, is it gonna like it? Nope. Alright, I guess we're just sticking with integers across the board. I could not tell you why it's not liking my types. Oh, this is probably because I'm doing a pointer. I think we would have been fine if I kept it as a generic. Oh well. Okay. Well, it ran at least. So at least we can debug it. So we see it prints 4725, which are the things to be inserted. It says it finds 7, but it doesn't print the found 11 because 11 is not in the list. And then we delete 2 and 4, and it seems to be fine and just print the 7 and 5. Okay, so our linked list seems to work. I mean, not with the generics, but it just, you know, in general, it seems to at least work as a linked list, which is fine. So those are our 3 main functions that we have. We talked a little bit about advantages and disadvantages of this last time, namely that it's like a dynamic array, pretty good for memory, and one thing that it has that's better than a dynamic array is the fact that we can get away with not allocating as much space every single time. Because if you remember, in a dynamic array, then we need to allocate space every once in a while, whenever we run out of room, that is, and like copy everything over. But with this, we can kind of just add nodes to the end as needed, and they don't all have to be next to each other in memory like any sort of array, which means that it's kind of nice in that we don't have to keep reallocating, but it does have this disadvantage of the traversal where we have to like jump across all of this stuff. So because of the fact that it's not all next to each other in memory, it's not as quick to access. One other thing about this that is not very great, which we're just going to go over here in a second, is sorting. So when you sort in a normal array, it's pretty simple because of the fact that you can do accessing just directly. You can just go straight to a memory space. So here's the new keyword. So if I have like a traditional static array or dynamic array, just an array in general, then everything is stored right next to each other in memory. And we've talked a little bit about the pointers involved with this. Really, there's just some pointer to the beginning of the array, and then whenever you use a number to access the array, like this, where you say r sub whatever, I, then all it does is start at wherever that pointer is, and then hop this many things over. And because it knows the size of these things, it can actually hop directly to there. So if I said r sub 2, then it knows to start right here, and then it knows the size of whatever data type this is. Let's just say an integer is 4 bytes. And so it'll say, okay, well, I need to hop 4 bytes times 2 spaces, so I'm just going to hop 8 bytes, which is right there. And so we can do it really quickly. It's pretty easy for it to access an array, just because of the fact that everything is stored right next to each other, so it's very predictable. But when we do a linked list, that's not the case, right? When we did that lookup, we actually had to do a traversal, where we start at the head, and then we follow these pointers until we reach either the end of the list, or we hit what we're looking for. So let's say we're looking for the number 6, we would start here, hop over, and then we would find it. And so the longer the linked list gets, the harder it becomes to actually look things up. And so this, if you're familiar with time complexity, which we haven't covered, or we don't cover in this class, and you haven't probably learned yet, but I know some of you have mentioned it before, this would be O of n, because it's going to need to go through n many things in the worst possible case, and this one is of 1. So the lookup and just general traversal is way, way better in an array than it is in a linked list. And because of that, when we actually do sorting, it becomes really bad when you're doing default sorting in a linked list, but there is one exception in which it's actually kind of better for this. So I'm just going to compare and contrast these. I think I'm just going to write the better example because the one that's bad is kind of annoying to program. It's not particularly hard, it's just kind of time consuming, and it's very, very slow to run. I think in a previous semester we had students program it, and it took like 5 or 6 times the amount of time to run than the normal array version. But let's just say I'm sorting and I have a linked list that already exists. We'll just say of integers for 7, 3, and 6. And we'll say we'll do something like bubble sort. So in bubble sort, you keep track of two things. You keep track of a pointer in the form of an index to whatever the current element is, and then you just look at the thing to the right of it, and you basically check, do I need to swap these two things? We check these two things, check if they're out of order. In this case, 4 and 7 aren't, so we wouldn't swap them. And then we go and point to the next thing, and we would say, okay, between 7 and the thing to the right of it, are those two things out of order? Assuming we're going in non-descending order, so it's least to greatest, then these things are out of order, which means we need to swap this 7 and the 3, right? Now this ends up being a little bit difficult when you do linked lists, because if you need to swap it, consider that I can't just swap these directly. I need to make like this 3 and that 7 there. I think the easiest way to do this is to actually not worry about these nodes at all and just make this 3 and make this 7. Like overwrite the data fields. That's the practical way to swap when you're doing sorting with linked list. But sometimes you don't want to do that for whatever reason. I would say that's always the best way to do it, but some people like swapping the nodes themselves. Potentially you might have things that actually rely on the pointers to the nodes, kind of like how we returned with the lookup that we wrote. You might have given other people references to these nodes. So if you're checking, or sorry, if you're overwriting these pieces of data and making this a 7, make that a 3, then if somebody originally has like a reference to this, like they just have their own variable called x or whatever that points to your node, then you may have just swapped it on them unsuspectingly, and now they have different data than they were expecting because of your sorts. And because of that, doing that shortcut is not always a great idea, even though it is faster and easier and probably generally a better idea. So if you give too much access to your linked list, then this is a no-go. Assuming we do that, then we actually have to swap the nodes themselves, and that's not fun. It's kind of difficult and very slow, super slow. So one way to do this is the way that was suggested in the semester that we actually programmed this, was to do a node lookup and then look up the two things. So look up the position I and then do the same thing. I guess I wouldn't really need the type, but I would set it equal to it and just grab these two things so that I have two pointers to these essentially. And then also do a third grab for this one. So we would do another lookup. We would do 3 lookups to get these 3 things and then just kind of update the pointers as needed. And that's really not good because the lookup is really slow, we just said, compared to an array. So this ends up taking forever to run. What you should also be able to do, and what I would suggest doing if you're ever going to implement this, is just keeping track of 2 pointers. I don't know where this came from, but I'm going to erase it. Oh, there's just a green thing on my screen now. Oh well. Is to keep track of 2 pointers, so one to the current object and then one to the thing that came before it. Kind of like how we did with the deletion. We just keep track of the current and then the next. And then whenever we hit what we're looking for, so let's say we hit these 2 and we figure out that we need to swap, then we just update using the previous and the current. So what I'm going to do is just say, let's say we write the bubble sort code, we get to the if check like we normally do, and we need to do the swap. So we say, you know, if the current data is less than, sorry, greater than, because I think I accidentally already swapped these. This was originally a 7 and a 3. I'm getting a little bit ahead here. This is 7 and 3, assuming they're out of order. So if the current data is greater than the current next data, which is basically our just r sub I is greater than r sub I plus 1 that we're used to in bubble sort. It's just written in a way that accesses a linked list. Then in order to do the swap, we're going to need to update some of these pointers. So what we're going to need to do is we're going to have these two swap places. So this is going to need to point to here. And this one is going to have to point to here. And now this, because 3 is going to come before the 7, is going to need to point here. And I'm sorry if this looks super messy. We'll reason it through as we go. And then we need to update this to point to here. So we need to update 4 pointers. So I'm going to erase all this so it doesn't look too messy. But what I would do is I would first keep track of this thing. So as soon as we get that match, I would keep a pointer to whatever the thing is. And then I would just update it like we said. So at this point, I think it's pretty safe. If you try to swap it without keeping a temporary variable, I think it becomes difficult. So I don't know. I'm just going to do it this way for now. So what we said we need to do is if this 7 is going to get moved to this position, then its next is going to be 6. And we need it to be pointed to by the thing that's going to go before it, which is 3. So in order to take care of that, we're going to need to make the currents next equal to swap rights next. And then after that, we would need to make swap right point to the current. So these two lines have done these two swaps. So what we did first is we said this one is going to need to go, and it's going to need to point to this thing now, since it needs to be moved around it, so that it's pointing to the list after this, to the right of this. And then the second thing we're going to do is we're going to update this to point to here, because the 3 needs to come beforehand. And we need to do it in that order because there was a dependency here, right? We were using the swap right next, the pointer that the swap right has, the 3 has, on the right-hand side of this thing. And so kind of like you would do with a normal swap operation in any sorting algorithm, you need to do it in this specific order, otherwise you're going to lose data. So we have that, and then we need to make everything else point correctly. So this 4 now needs to point to the 3, and then was that it? Do we only need 3? I thought I drew 4. This would swap over there. That would be here. I'm sorry, we do only need 3. I don't know why I drew 4 earlier. I don't remember what the other thing I said was. But the last thing we would need to swap is the previous and have it point to the swap right. I think that should be everything. You might be able to do this without 3 variables, but I'm just going to do it that way to be safe. And so we need to make this point to here. And again, this looks really super messy, but if we untangle this a little bit, then what we get is we have the 4 first, right? There's nothing pointing to the 4, and that what the 4 is now pointing to is the 3. And then the 3 is now pointing to the 7. And the 7 is now pointing to the 6. So this is what our linked list looks like now. And beforehand it looked like this, where it was 4, 7, and 3, and 6. Right, so if you do it this way, it's not as bad in terms of efficiency. I would definitely recommend doing it this way if you can. I don't think there's an issue with this. I'm pretty sure this works, if my logic is correct. And that's kind of how you're going to have to address swapping when doing something in a linked list like sorting. So it becomes a lot more hard to reason through than just doing the normal swap like you would in bubble sort. You just kind of use a temp variable. I mean, I guess realistically we only have about 3 lines of code anyways, so it's probably about the same in terms of runtime, but definitely harder to reason through, right? I would argue. So I think we should just go ahead and try to program this version really quick and just see if we can actually sort the list. So we'll pop over here, and what we need to write is a sort function. Sort. And we'll go ahead and write that down here. I'm just going to use bubble sort. I think it becomes really hard to write these too if you do things that aren't swap based, like bubble sort or selection sort, but I've never actually tried it. So linked lists in general I wouldn't recommend if you know you're going to sort something. Right, so I'm just going to create these two. We'll just do bubble sort for I equals 0. Oh, I would need to know the size of this, I guess, which is kind of annoying. Oh, actually the traversal ends up being a little different too. So writing bubble sort becomes super strange. Right, so bubble sort, the way we normally do it is we have like 2 for loops. The first for loop loops through the whole thing. Geez, let's see if we can actually do this. So node pointer, current, previous. Oh, I need this to be a pointer. And then what we want to do is, I'm just going to do 2 while loops. So we'll set the current equal to the head, and the previous will have to be, I mean, it can't be anything, right? So we're just going to have to leave it like that. And then we say while current No, we actually do need a thing for this, so we need to find the size first. Let's just write a function to do that really quick. It's going to be pretty much just the same code again. We just need to do a normal traversal. All this needs to do is increment the count. And then return it. And then we can kind of just do this the way we would normally do bubble sort, where we do go I less than the count, which we'll have to grab. So int count equals get size. Plus plus. So the first loop, if you remember, bubble sort just checks like how many things are sorted. We need to check that. Since this is a bubble sort, let's just do is sorted equals false. And then we need to do one run through the whole thing. So it ends up being a little bit weird to do a sort in this kind of thing. So we're going to have a mix of like a for loop and then an actual traversal. And you realistically could write this exactly like bubble sort if you wrote that get function that I mentioned that just goes through the array, or like does the lookup, basically just the lookup code. You could just write bubble sort normally, but it ends up being really, really slow. So we're going to try not to do that if we can help it. So this is essentially the same code that we had before. Actually, we can do another. I take it back. We can kind of do this almost exactly like normal bubble sort. Let's have the two loops like this: j equals 0, j less than count, j plus plus. So this inner loop goes through the list. And then with bubble sort, right, we said we start at 0 and then we go to count minus I minus 1 because there are I many sorted things. We would need to initialize the current to the head. I'm realizing this is going to be really janky. But we need to start at the count head and then kind of like work our way forward. So we'll do current equals current next. And then what we have to do is check if the two things are out of order. Then we would need to swap them. So far this isn't too bad, I guess. So if the current data is greater than, the way we're going to do I plus 1 is with the next because that's the pointing to the right thing. Data, then we need to do a swap. And then we would need to do the swap that we just mentioned. One thing that just popped into my mind is the fact that if our swap involves the head, then we actually need to update the head. So I think we should check for that, but let's just copy over the code I had here. So I just started a new thing called swap rights that pointed to the thing to the right that we wanted to swap. And then we did this in a specific order. So we set the current next equal to swap rights next, which I guess would be current next next. Yeah, I think this is still probably an easier way to do this. And then we set swap right next equal to the current. And then we set the previous, which we also need to keep updating, I guess. Did I keep a previous? I call it prev. We set the previous next equal to swap right. Okay. So we need to do some things here with previous. I haven't been updating that. So what we need to do is check if previous equals null pointer. I'm just going to do it that way. Then previous equals head. Actually, no, I'm sorry. I'm overthinking it. We can just do that this way. Set the previous equal to the current, and then that's good enough. Okay, so that I think addresses our issue with the head. And so if we're swapping, if the previous is null pointer, then that would imply that we're swapping the head, which means that we should check for that. So if previous is the null pointer, the head then what we need to do is we need to make the head equal to swap right, else this. And it's giving me a warning, but it should be fine because this should be dereferenced. Yeah, okay, so I fixed it. All right, so this is a little hard to follow, I apologize, but what we're essentially saying here is we're going to keep a pointer to wherever we are in the list. By default, we're starting at the first element in the list, and we're having the previous equal null pointer. I'm sure there's like ways you could optimize this and write this better, but I'm kind of doing it on the fly here. And then what we're going to do after that is we're going to go through the list like we would normally with bubble sort. If we find that two things are out of order, we're going to swap them. But we have one exception, which is when we have the head that we're swapping, because of the fact that the head is going to be like a separate pointer because it's a class member. So if that is the head, which is only when previous is equal to null pointer, because that's what we initialize it to, that's only happens the first time that you go through this inner for loop, then what we need to do is we need to update the head as part of this swap rather than the previous pointer, because we don't have a previous pointer yet. Otherwise, if we do have a previous pointer, we could just swap like we said normally with that whiteboard we wrote, and then these two just update them to point to the next thing, to the right of where they were before. So if I'm not mistaken, I think this is fine, and we'll sort it, and I'm sure we could optimize it a little bit, but this is definitely better than using a lookup and just writing it normally, like just standard bubble sort. Let's just make sure this works. We'll say list.sort, and then we'll print the list. And we'll see if it works. And hopefully it doesn't take fault. I do think this is a kind of difficult code. I know a lot of students had issues with it in the semester that we gave it. I think we have an infinite loop because I am never breaking. So if we pause here, I'm assuming... Oh. So it grabs that. Oh, I'm never updating it. Whoops. That's just the problem with the get size. Yeah, so make sure you always have this code here that updates the current pointer. My bad. Okay, we do get a seg fault, so obviously I'm doing something wrong. So current is pointing to 5, and next is pointing to nothing. Okay. Maybe my count is 1 bigger than it needs to be? No? 4? I think that's right, right? We have 4 things in the array, and 5 is the last one. I starts at 0, minus 1. So this should go from J2. Right. No, there is an issue with this. I think I'm just going to leave this here. In hindsight, if you ever want to write swap with this, I remember now why it was such a big deal when we wrote this before. I'm sure we could fix this and finish writing the code. The issue with this is because of this loop here. Actually, let's see if we can fix it really quick. Because of this loop here, it is assuming that we can just go through the array in like a normal manner, which is how you expect to sort just in general. But because we're doing a swap, the current pointer is going to end up getting messed up because it's going to get swapped over. So consider if I had this code here, wherever it went. Nope. Okay. So I have something like this, and I go to do the swap, then we kind of encounter an error. Because if we have that scenario, so let's just say we have those 3 nodes that we said we're going to try to swap here, like this, where this one is the current, this one is the current next, and then we keep track of the previous, like we said. Then once we swap it, what we've done is we said this points to here, this points to the other side, and then this one points to here. Which means that the order that it ends up being in is like this, where the 2 things that we're trying to swap end up getting swapped, which is totally fine. It's kind of what we expect, right? But this ends up being the current, and this was the previous current next. I think we just called it swap right. And this is previous. And so if you notice, by doing this swapping process, what we've accidentally done is we've moved the current 1 ahead of where it's supposed to be because we swapped it to the right, and because we're using pointers, it followed along with it. So what I suggest we do is we just fix that really quick. So what I'm going to do here is say current equals swap right. And what I hope will happen is that that will fix this problem, and we still get our efficiency. Okay, well, somewhat there. You can see it swapped everything to the right of 4. It like sorted that correctly, just not the 4. So we kind of got things okay. It's just slightly off. And while we're on this topic, there's I guess a programming concept to mention, which is just like complexity of what you're programming. So I said earlier, like that other strategy is really inefficient and horrible, but it's also not hard to program. And so like obviously this is really tough. Like, you know, if you don't fully get how to program this on your own and like forget this from this lecture, totally understandable. It's totally fine when you're programming things to sometimes go for an easier solution to program than to go for something that's more efficient, because you just save yourself the time. So just consider there's no shame in that, even in a professional setting. That's totally fine. You end up saving yourself time on your programming if you don't do anything too complicated. So yeah, don't ever be afraid to go for something easier, even though this seems a little ridiculous. And so I think our issue is with this. The head just never seems to swap. I imagine it's because of this part. Oh, you know what? No, it's not. The issue is because I didn't update the assorted thing. So it's only doing one loop through, I think, is the issue. Equals false. Okay. Closed, and now it is sorted. Okay, so that was just a small typo. And there we go. So this is a really efficient way to sort a linked list. Again, if you think this is hard, that's totally understandable. This is probably one of the more difficult things we're going to do. If you ever just want to do bubble sort and just use the lookup function instead of the normal array accessing thing, totally fine. I will not fault you. But it will run like 10 times slower, I will say in advance, just from experience. Okay, so that took quite a while, but that was our sort for a linked list. That's how we do it efficiently. I want to talk a little bit. Yeah, and question in chat, are you going to post this code? Yeah, I will post this code, and I don't expect it to show up on any homework, but I'll comment it before I upload it too, because I'm sure, like, looking at this right now, it's probably just a bunch of mess. So I'll try to explain it in the comments as well. All right, so I just wanted to go over one closing thing on linked lists, or at least standard linked lists, which is just the ability to implement them with recursion. We've said previously that you can do anything that you could do with a loop with recursion, and so linked lists are no exception to that. And realistically, they're actually not too bad. I think linked lists with recursion aren't particularly hard, with the exception of deletion. So I just want to talk about that a little bit. Let's do insertion really quick, and then we'll do lookup, I guess. I'll probably program these. I think we'll just spend the beginning of next class doing it. So I think we have a little bit of free time. On that note, from previous experience, I think we'll probably finish all the topics on the syllabus and still have like 3 or 4 classes left over. I was just thinking about that recently. So I'm expecting to go through all the material within the next 2 weeks, I'd say. And so we'll have a little bit of free time. If there's any topics you want me to talk about in just general computer science or programming, then feel free to make a suggestion. I'll probably make an announcement on Canvas and just give like a list of topics that I'd be comfortable talking about. That way we can just, do stuff that won't be on an exam, but kind of prepare you for either just, hobbies or future classes. Anyways, let's say we want to do insertion and we want to do it recursively. I actually think this is not too bad to program, but again, recursion is sometimes hard to wrap your head around, so that's our issue. What we say when we do an insertion is that we want to create a node and then put it at the end of the list. So ideally, we create some sort of new node which contains whatever it is that we want to hold, and then what we do is we update the end of the list to be here, right? So as far as the recursion goes, what we need to do is we need to find a way to get to the end of the list, and then just for the sake of problem solving, let's try to frame it in such a way that we can reduce the problem and that it recurses on itself, and that we're solving a problem that's smaller but still kind of just the same problem. So the way I propose we do that is I want to insert something into a linked list, and what I want to do is insert it at the end and into a list that's progressively going to get smaller. So what I want to do here is say, let's try to insert into the list starting at the head. So I think as far as our function goes for insertion, we're going to need to keep track of 2 things. We're going to need to keep track of the thing that we want to actually add. We'll just say T again. I'm going to assume that the generic works for whatever reason it does in my code. And then we're going to keep track of whatever the current pointer is to the current node. And so if we think about it recursively, then our problem is we need to insert this into a list. And if it doesn't work on the current node, what we need to do is insert it into the list to the right of it. So we kind of need to like pass it along until it reaches the end of the list. Another way to think about this recursion in terms of that reduction operation that we've talked about before is we need to get this down to something that's trivial to solve, and something that's trivial to solve is when the list you are inserting to is empty. Because if you insert something into an empty list, then it's really easy because you just put it right where it needs to go. As opposed to inserting something into a big list, which involves moving all the way to the end. So our reduction here is that we need to reduce it in such a way that whatever the list that we're looking at is going to be nothing. So the way that I suggest we do that is we just check if current next is equal to null, then put the thing in. We'll actually code this. I'm just gonna do that for now. And then else what we need to do is then put it into the list to the right of this. Insertion. Object. And then we need to put it into the list to the right of this one. Right. So one thing with recursive thinking is the ability to break this down into solved problems so that part of your problem is smaller. One thing that I'd argue for this is that if I was to cut off this head here and just remove it, then the thing to that right of that head is still a linked list. And if I did the same thing with this, the thing to the right of this is still a linked list, right? And you're still trying to insert something into a linked list, therefore it's still the same problem that we're trying to solve. And so what I think here is a good way to think this through is if I want to insert something into this list, and I'm not able to do it because I'm not at the end, what I want to do is then try to insert this object into the linked list that's to the right of it, such that the next pointer becomes the head of that linked list. So consider if I was to just ignore this, then the head pointer of the linked list to the right of it is the next node. And so our problem here, our recursive case, is trying to insert something so that the next thing to the right of it is the head of the linked list that we're trying to solve for or trying to do the operation on. And I think that's generally going to be the case for all of the recursive code that we do for this. But that's just my general reasoning behind why we do this. So this right here is saying insert the object into the linked list that exists to the right of the current linked list that we're looking at. Else we have the base case. So just as a refresher, we have those three parts to recursion. That was the base case, which told you where to stop. It was the thing that you're able to solve. In this case, that's if our list to the right is null. In other words, if our list is empty, then that's a super easy problem to solve. You just throw the thing into the empty list. Otherwise, we need to do some recursion. So we can see that this function calls itself. That's the recursive case. And then we said that we always have a reduction operation. Can somebody figure out what that is here? So I'll ask you guys, what part of this code does the actual reduction in this case? I'll kind of give you a hint. With the other functions that we've been doing recursively, generally your reduction operation ends up being an argument to your recursive function call. So knowing that hint, it's either the object part or the current next part. So this is definitely not doing anything, it's just passing an object, but that ends up being our reduction operation. And the reason that's a reduction operation is because it's doing that reduction of the list. We said here with our thinking that this is, again, going to try to insert it into the list to the right of the current one by following this pointer. So if we start at this head, if we follow the pointer to the right of it, we end up at a list that is one smaller than our current list, which means that we end up with a smaller list, and that is reducing the problem closer to our base case, which is to get a list of size 0 to insert something into. So this right here is a reduction operation. And again, just as a reminder, we said that reduction seems to imply like subtraction, but that's not always the case. In this scenario, the reduction is the reduction of the size of the array, but that's done by following a pointer, which is not subtraction. Again, I keep bringing this up because it's almost guaranteed to be a test question. You aren't always going to do reduction operations with subtraction. It is sometimes done with other things. Here. Right, so do we want to try to program this? We got 3 minutes left. Nah, I think we'll try to program it really quick. I might post some code for this as well. I did an assignment for this idea in a previous semester, except I did it with like nesting dolls. And so you're able to like follow the nesting dolls recursively inside of each other. I might post that code just if you guys want to take a look at it. But let's try to program that in these last 3 minutes. I want to basically just do these same 3 functions again, but do them recursively. So for insertion, we said we need to have the thing that we're inserting, and then we need to keep track of the current thing, node pointer current, and then we're probably going to need to do that for these two as well. And deletion is probably going to need both a current and a previous. Okay, so let's try to write this really quick. At least the first one. I don't think we're going to have time to test it because we would need to have all these written. Okay, so our general idea here was that we wanted to check first if the current next is equal to null. Actually, sorry, there was one other thing I wanted to mention about this. Another view for this, if you want to look at it from a programming, or sorry, like a problem-solving point of view, is that we're trying to recurse every single time, and this is just like an error check to make sure that you don't recurse in a bad case, because consider if you were to pass null to this, then you're trying to access like a null array, so you can kind of consider this to be like an error check. If the current thing is going to be a null, then don't do the function call, because that's unsafe, is another way to view this kind of code. But if we do that, then we say if the current next is equal to null, then we're at the end. And then we can do the recursive case pretty easily. Otherwise, we need to insert the data that we're trying to insert in the list to the right of this, which is the current next. Okay, so let's just do this really quick. I'm also realizing we do need to consider the case of when we're inserting into the head. Actually, no, we don't. This takes care of itself. I'm sorry, overthinking things. Let's just finish it. What we need to do is we need to make no, I'm sorry, I was right. We need to check this. Oh yeah, I need to separate these. I'm sorry. I'm realizing something way too late. I'll explain it, I guess, more next class. I'm going to do an extra check to see if current equals null, and this is our check for the head, essentially. Which might not seem obvious at first, but I'll explain it more next time. So in that case, current next equals a new node, where we use the data to make it and put it in, and then otherwise the current next equals new node. include data. So I guess I don't need these. Okay, but that is generally what the code is going to look like. I'll explain this more next time while we're doing this extra thing. Basically just to check for the head. Okay, so looks like we're out of time. If you have any questions, I will stick around a little bit and we'll finish this code up next time. So I will see you guys all on Thursday.